distance between slits, coherent sources. Slit or coherent sources, we can say distance between coherent sources and screen. And D is distance between two coherent sources. Now see, this lambda is of the order of 10 to the power minus 7 meter. No? This lambda is suppose 4000 Armstrong or 400 nanometer to 800 nanometer. That means it is 4 into 10 to the power minus 7 meter. So wavelength is this order. This capital D we can keep of the order of suppose 1 meter or maximum 1.5 meter. If it is more than that, intensity will go down and we will not be able to see anything. So it can be of the order of 1 meter. Now if you are taking this one of the order of even millimeter also, if the distance between two sources is of the order of millimeter, then also the fringe width will become of the order of 10 to the power minus 4 meter, not even millimeter. So it can't be visible by naked eye or without any special arrangement. By using telescope or by using microscope, we can see. We can't see, means directly we can't see on the screen. So for this larger fringe width, what should be? This D must be large, but there is limitation. We can't increase too much. And this small d should be very less. This we can do. We can change this position. So these two slits are very close to each other. It must not be more than of the order of millimeter, we can say. Maybe 5 millimeter, 4 millimeter, like that practically. It should not be more than that. Otherwise, the fringes will be very small, not even line. Thickness of the fringe will be much less than, if this line you are drawing, the thickness of the line is maybe 2 millimeter, we can say. Or with the pen you are drawing, then also it will be of the order of 1 millimeter. So your fringe will be less than that if D is not of the order of millimeter. So this small d must be very small. That's why the two coherent sources are very close to each other. So these are the ways by which we can increase fringe width. Now sometimes we ask what will happen if this such things happens. What will happen to the fringe width if distance between slit and screen is increased? Naturally beta will increase. What will happen if violet or blue light is changed by red light? In case of violet light, lambda is less. In case of red light, lambda is more. So what will be? Fringe width will increase. So when we change the wavelength, then also fringe width will increase. D, if increases, the distance between two coherent sources increases, then fringe width will decrease. Now sometimes it is asked, the whole apparatus is completely immersed in water. What will be the effect? If the whole apparatus, suppose we have done the experiment with sodium vapor lamp, that is monochromatic source. maybe 5893 angstrom at fixed wavelength. Actually, two are there, 5890 and 5896, but average we take 5893. So, if we have done the experiment in air and the whole apparatus is completely immersed in water, what will be the effect? So, in that case, still we will get same pattern, but this lambda will change. When light enters into water, its wavelength decreases. Wavelength decreases means fringe width will also decrease. So these are the sometimes reasoning question is asked. What will happen when this is done? So these are the 3-4 things. One mass question is asked. So practically we have got only one option, that is small d. We can't increase capital D much more because that visibility will be, or intensity of light will be very less. We will not be able to see the interference pattern. This has got the limitation. We can't increase. In case of light, maximum is 800 nanometer. We can't increase, go beyond that. So naturally the third option, that is small d, that we can change. So that's why small d, that is the distance between two slits, is kept very small in order to get the fringes of, means which is visible. If the fringe width will be very less, it will not be visible because our resolving power, you are knowing, we have done in telescope. So telescope has also got a limitation of resolving power. So the fringes will not be separate. It will not be visible separately. Okay, there is alternate method also. Sometimes we use this one to solve the numerical, especially when more than two sources are there. For competitive exams, sometimes we ask. To find relation between x and delta. X means, what was the x we are knowing? So if derivation is asked, the previous one we will do. The derivation is in our syllabus. What we have done yesterday, that is in our syllabus. This one also will know. Suppose these are, this is S1, this is S2, this distance is D. Here is a screen. This distance is capital D. We are considering any point P. Where the two waves are superimposing. From here the wave is going like this, and from here also the wave is going like this. So for different points on the screen, this phase difference between the two superimposing waves which is arriving here will be different. So this distance one x. Now this S2P square can be so this is d by 2 from here to here, and this is also d by 2. S2P means this square plus this square. S1P b square plus x x minus d by 2 whole square. This square plus this square, this one only. If you subtract these two, this square minus this square, s2p square minus s1p square will be now this s2p minus s1p into s2p plus s1p a square minus b square.
Sir, please place the camera a little bit down, sir. Yes, sir.
So this one will come how much? X square and d square by 4 will be cancelled. What is left? Here will be xd and there also xd, that is 2xd will come. So this is delta, path difference, s2p minus s1p, which we are interested to find. So this will be twice xd over this. Now if point P is very close to O, then this d is a very small, we are knowing, it is of the order of millimeter only, it cannot be beyond millimeter. So d is very small. And if P is very close to O, then this S2P plus S1 S2P plus S1P will be approximately 2D. So delta will be how much? Twice xd by 2d, that is xd by d. This we have already done by that way, or you can find by this way also. And after that, same condition. For P to be bright, what will be? This must be equal to n lambda. Or P to be dark, this must be equal to 2n minus 1 lambda by 2. After that, same thing will happen. Only the first part you can change. Whatever we have done by angle, if you are not interested to that, you can do by this simple algebra. Okay. Salaram? Now, suppose this is the screen. It may be a white paper, white page, white cloth, whatever it is. So on this screen, what will you get? If the slit is rectangular, we will get bands. If slit is hole, we will get circular ring, that we have already explained. And this band will not be of the order of millimeter. Just now we have seen by calculation, it is of the order of 10 to the minus 4. So not even a line. Here we are representing that band by very wide, just for understanding. Suppose this is the central band. So this point is our O. This is first one, this is second one, like that. Suppose it is like this. Okay, so this is the situation. So these are lines we represent dark, where intensity is minimum. And this dotted line we are representing where intensity is maximum. This whole is bright. In the bright also, what will be at some places, suppose here intensity is 4i. At this place intensity is 3i, this place 2i, this place I, and then finally it is 0. Similarly, down also, maybe 3i, maybe I, then again 0. So bright means we are considering this one, where intensity is maximum. And this is our dark. So this is central bright. This is first dark. This is second dark. This is third dark. This is fourth dark. Similarly, this side also. First dark, second dark, third dark, and the fourth dark, like this. So this we will say, this line, this is here again maximum, that is, this is bright. We are getting light from here to here. But light is maximum at a particular point or in a particular line. And that only we say bright. That is the meaning of bright. Means where intensity is maximum. So this is B1, this is B2, second bright, this is third bright. Similarly, this side, B1 dash, now suppose you are asked or you are given in the numerical distance between third dark or distance of third dark from the center bright. So distance of third dark or position of third dark, whatever it may be, position of third dark from the central bright is 5 millimeter. What does it mean? What is given this? What is this? Is this lambda? Is this capital D? Is this small d? Is this beta? What is this? Central bright to third dark. Central bright to first bright. Beta. No? From here to here. Suppose this is beta by 2. From here to here, this is beta. This beta is of the order of millimeter only. Maximum it can be millimeter. So you think, don't think that this is this wide. Not even the width of line. We will have to magnify, then we can see. We will not be able to see by our naked eye. Okay. So this is the meaning beta. So what is this given? Is it 2 beta? Is it 3 beta? Is it 5 beta? What is given that? Yes. What is given in this? First dark to third dark. What is this? 2 beta. From the central bright is given. So it is 2.5 beta. So that means you are given here 2.5 beta is 5 millimeter. Now suppose you are given if fringe width is beta, find distance between second dark on both sides of central bright. What will be the distance? Yes. Second dark. This is central bright. Second dark means here 1.5 beta. Similarly from this side also 1.5 beta. So this distance is 1.5 beta plus 1.5 beta. So it is 3 beta. Distance between second dark and sixth bright. What will be on same side? It can be opposite side of the central fringe also. Suppose this is the case. What will be? Sixth bright, from the center it is 6 beta. Second dark 1.5 beta. So it is 6 beta minus 1.5 beta. So 4.5 beta. So in the numerical directly you will not be given that fringe width is this much. This type of case will be given. So you have to decide what will be the value of beta from that. Suppose this is given distance between second dark and sixth bright on the opposite side of the central bright is 7 millimeter. Find the beta, or D is given, a capital D is given, find wavelength. So indirectly from this line you will find beta. Understood? Now what will be the effect on fringe pattern? Fringe pattern and fringe width. Okay, I'm giving small beta. When one of the slit is covered by transparent sheet of thickness T and refractive index mu. Okay. So when one of the slit is covered by transparent sheet, if one of the slit is covered by black paper, what will be? No interference. Then intensity will be uniform everywhere, as we are getting due to one source of light. So suppose this is the two slit, one of the slit is covered. Earlier the light was coming this way here and we are getting the central bright. Why we are getting central bright here earlier when it was not covered with transparent sheet? Because the path difference was equal. This S1O and S2O was equal earlier. So we are getting central bright here. Now, due to the presence of this transparent sheet, its equivalent path length will be different. I think we have not done optical path or not. No. Optical path, you must know. Suppose light is passing through any denser medium. This is the thickness T. So, equivalent distance traveled by light in air, that we call optical path. That means, suppose it takes some time, whatever time is there, to cross this one. During that time, how much distance is covered in air? That is optical path. Should we continue or leave?
Leave, sir.
Leave.
Yes,
This
sir.
was easy. Yeah, this is Ila. Okay, so next day we'll continue from here only.
Sir.
Huh?
You know me so nicely.
Mm.
Thank you, sir.